Hello viewers, today we will discuss a new topic called data representation and basic computer arithmetic. To be more specific, in it we will discuss number system and complements. So, let us begin with number system. When we type some letters or words, the computer translates them in numbers, as computers can understand only numbers. A computer can understand positional number system where there are only a few symbols called digits, and these symbols represent different values depending on the position they occupy in the number. The value of each digit in a number can be determined using number 1 the digit, number 2 the position of the digit in the number, and number 3 is the base of the number system, where base is defined as the total number of digits available in the number system. We will discuss various number systems one by one. First one is decimal number system. The number system that we use in our day to day life is the decimal number system. Decimal number system has base 10 as it uses 10 digits from 0 to 9. In a decimal number system, the successive positions to the left of the decimal point represents units, tens, hundreds, thousands, and so on. Each position represents a specific power of the base 10. For example, the decimal number 1, 2, 3, 4 consists of the digit 4 in the units position, 3 in the tens position, 2 in the hundreds position, and 1 in the thousands position, and its value can be written as you can see in the figure. Here it is given 1 into 1000 plus 2 into 100 plus 3 into 10 plus 4 into 1, which is equal to 1000 plus 200 plus 30 plus 4, which is equal to 1, 2, 3, 4, that is 1234. As you can see, each digit is multiplied with the powers of 10 because it is a decimal number and ultimately we get the original number. Let us now see how to convert other base system to decimal number system. The steps followed in it are: first step, multiply the digits of the given number with the powers of the base of the given number, where power starts from 0 and go up to n minus 1, where n is total number of digits. Step number 2, add the results of step 1. Let us begin with the other base system, starting from the binary number system. Binary number system has base 2 as it uses 2 digits 0 and 1. Let us understand it with the help of an example in which we convert it into an equivalent decimal number, as you can see in the figure. In this example, 10101 is the binary number. In order to convert it into a decimal number, we multiply each digit of the number with the powers of 2 as shown in the figure. Here in step 1 we have 1 into 2 raised to power 4 plus 0 into 2 raised to power 3 plus 1 into 2 raised to power 2 plus 0 into 2 raised to power 1 plus 1 into 2 raised to power 0, which is equal to 16 plus 0 plus 4 plus 0 plus 1, which is equal to 21. Next is octal number system. This number system uses 8 digits 0 to 7, so its base is 8. Again, let us look at the figure. In this example, 12570 is the octal number. We convert it into an equivalent decimal number by multiplying each digit of the number with the powers of 8 as shown in the figure. Thus, 5496 is the equivalent decimal number. Here in step 1 we have 1 into 8 raised to power 4 plus 2 into 8 raised to power 3 plus 5 into 8 raised to power 2 plus 7 into 8 raised to power 1 plus 0 into 8 raised to power 0, which is equal to 4096 plus 1024 plus 320 plus 56 plus 0, which comes out to be equal to 5496. So, then comes hexadecimal number system. This system uses 10 digits and 6 letters 0 to 9 and A to F respectively. Letters represent numbers starting from 10. A is equal to 10, B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14 and F is equal to 15. Look at the figure. In this example, the hexadecimal number is 19FDE. We convert it into an equivalent decimal number by multiplying each digit of the number with the powers of 16. Thus, we get 106462 as the equivalent decimal number. Here, in step 1, we have 1 into 16 raised to power 4 plus 9 into 16 raised to power 3 plus F into 16 raised to power 2 plus D into 16 raised to power 1 plus E into 16 raised to power 0, which is equal to 1 into 16 raised to power 4 plus 9 into 16 raised to power 3 plus 15 into 16 raised to power 2 plus 13 into 16 raised to power 1 plus 14 into 16 raised to power 0, which is equal to 65536 plus 36864 plus 3840 plus 208 plus 14, which comes out to be equal to 10646210. From the examples we have discussed so far, we can conclude that in order to convert a number from one base to decimal number system, we need to multiply the digits of the given number with the powers of base of the given number. There are many methods or techniques which can be used to convert numbers from one base to another, like first of all we have decimal to other base system. The steps followed in it are: step number 1, divide the decimal number to be converted by the value of the new base. Step number 2, get the remainder from step 1 as the rightmost digit of new base number. And in step 3, divide the quotient of the previous division by the new base. Step number 4, record the remainder from step 3 as the next digit to the left of the new base number. Repeat steps 3 and 4, getting remainders from right to left until the quotient becomes 0 in step 3. The last remainder thus obtained will be the most significant digit of the new base number. Look at the figure to understand it. In it, we are converting the decimal number 29 into a binary number. Here, in step 1, we divide 29 by 2, getting the result 14, which is nothing but quotient and remainder is 1. Then we divide the result obtained in step 1 again by 2, getting 14 as the new result and 0 as the remainder. Again, 7 is divided by 2 to get 3 as a result and 1 as remainder. Then 3 is divided by 2 to get 1 as a result and 1 as a remainder. At last, we divide 1 by 2 to get 0 as a result and 1 as remainder. So, once we get 0 as a result, we stop there. Scanning the remainder values from bottom to top, we get the binary number. Keep in mind, as mentioned in steps 2 and 4, the remainders have to be arranged in the reverse order, so that the first remainder becomes the least significant digit and the last remainder becomes the most significant digit. Thus, the binary equivalent of the given decimal number 29 is 11101. Similarly, we can convert a decimal number into octal or hexadecimal number system. Next is, if we want to convert other base system to non-decimal system, then the steps that needs to be followed are: step number 1, convert the original number to a decimal number with base 10. Then in step number 2, convert the decimal number so obtained to the new base number. For example, we want to convert 25, an octal number, into a binary equivalent. This can be done as shown in the figure. Here, as we can see, first of all, we convert the given octal number 25 with base 8 to decimal number by multiplying the digits of octal number with the powers of 8 and then adding the terms. We get 21 with base 10 as the decimal number. Now, we need to convert 21 into binary number. For decimal to binary conversion, we need to follow the steps as were recently discussed in the previous example, and finally we will get 10101 as the binary number. This is how we convert a number from one base where base is not decimal to some other base number. Now, let us do the same conversion using a shortcut method. The steps that are followed in it are: step number 1, convert each octal digit to a 3-digit binary number. The octal digits may be treated as decimal for this conversion. Step number 2, combine all the resulting binary groups of 3 digits each into a single binary number. Look at the figure to see how this conversion is done. Here we have 2 digits 2 and 5. We convert each of the digit into 3-digit binary numbers, and ultimately we obtain 010101, which is a binary number. Thus, we can directly convert an octal number into binary without the need of converting it into a decimal number. I hope it is clear to you. Similarly, we have shortcut method for binary to octal conversion. Various steps followed in it are: step number 1, divide the binary digits into group of 3 starting from the right. Step number 2, convert each group of 3 binary digits to one octal digit. For example, let us convert binary number 10101 to octal number as shown in the figure. Here, as you can see, first of all, make pairs of binary digits starting from the right, where size of each pair is 3. Then convert each pair into its decimal equivalent, and finally, we will get 25 as the octal number. So, next is shortcut method for binary to hexadecimal. The steps followed in it are: step number 1, divide the binary digits into groups of 4 starting from the right. Step number 2, convert each group of 4 binary digits to one hexadecimal symbol. For example, let us convert binary number 10101 to hexadecimal number as shown in the figure. Here, first of all, we create pairs of binary digits with size of each pair equal to 4. If number of digits remaining on the left comes out to be less than 4, then append zeros in front of them to make the pair of size 4. Then find decimal equivalent for each pair. Thus, we will get a hexadecimal number 15. Similarly, we can convert a hexadecimal to binary number using the shortcut method. Various steps followed in it are: step number 1, convert each hexadecimal digit to a 4-digit binary number. The hexadecimal digits may be treated as decimal for this conversion. Step number 2, combine all the resulting binary groups of 4 digits each into a single binary number. For example, let us convert hexadecimal number 15 to binary number as shown in the figure. Here, First of all, we write a 4-digit binary number for both 1 and 5. Keep in mind, now we are treating 1 and 5 as decimal numbers. Then combine all the binary numbers, we get 0, 0, 0, 1, 0, 1, 0, 1 as the binary equivalent. With this, we complete number system. Now let us learn complements. In it, let us first of all learn signed magnitude representation. The signed magnitude representation is very intuitive. The most significant bit MSB represents the sign of the integer and the remaining bits represents the magnitude, that is the absolute value of the integer. For example, as you can see in the figure, using a 4-bit signed magnitude representation, we can represent 3 as 0, 0, 1, 1, where MSB 0 means positive, minus 3 as 1, 0, 1, 1, where MSB 1 means negative. Note that 0 can be represented in two different ways. It can be either 0, 0, 0, 0 or it can be 1, 0, 0, 0, where MSB 0 means positive and MSB 1 means negative. The sum of two positive integers can be computed as shown. In this representation, applying a bitwise long head addition for all except the sign bit and simply copying the sign bit results in the signed magnitude representation of the correct result. In this case, sign bit is 0. The same method computes the sum of two negative numbers as shown in the figure. Here, again copying the sign bit and applying a bitwise long head addition for all other bits renders the representation of the correct result. In this case, sign bit is 1. However, the same method cannot be used to add two numbers with different signs. To know the sign of the result, the adder would have to compare the magnitude of both the numbers. Subtract the smallest magnitude from the largest magnitude and assign the sign of the argument with largest magnitude to the sum. Clearly, using the signed magnitude representation will complicate the adder hardware. For example, 3 plus minus 4 will result in a negative sum. So, the sum's MSB should be 1. So, what we do here is that we subtract 3, that is 0, 1, 1 from 4, that is from 1, 0, 0. We will let 0, 0, 1 as the magnitude. Also, we know that 4 is greater than 3 and its sign bit is 1. So, we affix 1 in front of the magnitude obtained. Thus, we will get 1, 0, 0, 1 as the answer. Then comes 1's complement representation. In 1's complement representation, positive integers are represented as in signed magnitude representation. Negative integers are represented by flipping all the bits of the representation of the corresponding positive integers. For example, in 4-bit 1's complement representation, we have, as you can see in the figure, plus 3 which is equal to 0, 0, 1, 1. Reversing its digits, we get 1, 1, 0, 0 which is equal to minus 3. Similarly, we have plus 7 equal to 0, 1, 1, 1. Reversing its digits, we get 1, 0, 0, 0 which is equal to minus 7. Note that 0 can still be represented in two different ways. Like 0 can be represented as 0, 0, 0, 0 or 0 can be represented as 1, 1, 1 and 1. As for the signed magnitude representation, we can easily check whether a number is positive or negative by examining the MSB. Adder hardware using the 1's complement representation is still not really simple though. Hope 1's complement is clear to you. Now, we are going to study 2's complement representation. In 2's complement representation, positive integers are represented as in signed magnitude representation or 1's complement representation. Generating the representation of a negative integer is done in two steps. First step is find one's complement of all the bits of the representation of the corresponding positive integer. And step number 2, add 1 to the result. For example, in 4-bit 2's complement representation, we have, as you can see in the figure, 3 is equal to 0 0 1 1. Then 1's complement of 3 will be 1 1 0 0. Adding 1 to it, we get 1 1 0 1. Similarly, 7 is equal to 0 1 1 1. Then 1's complement of 7 will be 1 0 0 and 0. Adding 1 to it again, we get 1 0 0 1. The MSB still represents the sign bit, and there is only one representation of the number 0, that is 0 is equal to 0 0 0 and 0. Then 1's complement of 0 is 1 1 1 and 1. Adding 1 to it, we get 0 0 0 and 0, because 5th bit is discarded. So, this is how numbers are represented in 2's complement form. Now, coming to the next part, detecting the overflow. Overflow occurs when more information is being transmitted than the hardware can represent. For example, a natural number which is larger than 2 raised to power 32 plus 1 cannot be represented with standard 32-bit natural number representation. Also, if we want to represent a real number 3.141592, it is impossible to represent it precisely using a finite number of bits. In such cases, overflow occurs because the hardware of the computer cannot correctly represent the information that is being passed on to it. When adding numbers, overflow can occur if the sum of two numbers falls outside the range of the numbers that can be represented with 32 bits. Indeed, even if both the numbers fall nicely inside the representable range and can be correctly represented using 32 bits, their sum might fall outside the range of numbers that can be represented with 32 bits. So, the sum cannot be correctly represented by the hardware using 32 bits. Now, let us see how to detect overflow in numbers. For numbers, overflow can be easily detected by checking for a carry out of the MSB. This is illustrated in the example as shown. The 4-bit natural number representations of 8 and 9 are 1000 and 1001 respectively. We know that 8 plus 9 is equal to 17, where 17 can be represented as 10001. Note that representing 17, the sum requires 5 bits. It cannot be represented with 4 bits. So, overflow occurs. When addition hardware computes the sum, we get as shown in the figure. The 5th one is the carry out of the MSB. Since it cannot be represented, it is lost, and the result computed by the hardware becomes 0001, which represents 1, not 17. Since there is no way to represent 17 with 4 bits, overflow occurred and the computed sequence for the sum does not represent the correct result. So, whenever we need to perform addition of two numbers, we must ensure correct number of bits are chosen for the representation. Otherwise, we will get an incorrect output. So, with this our lecture is over. So, finally concluding the lecture, today we have learned various number systems, their conversions, we have learned signed magnitude representation, 1's complement representation and 2's complement representation of numbers. So, I hope you have understood the lecture. In the next lecture, we shall learn fixed and floating point representation. Also, we will discuss character representation. With this, I sign off. Thank you. Have a nice day.